Hello everyone. In this video we will go through another example for designing the controllers using the frequency domain. The system which is provided for us is given as a transfer function of 1 plus 10s over s times 1 plus s squared. So we can see that we have a 0 at z equal to minus 0.1 and we have 3 poles which are at 0 and P2 and 3 are at minus 1. And we are supposed to design a controller such that first of all the controller that we have is either a proportional one or a first order controller. Then we need to have a steady state error for a step reference being equal to 0. The crossover frequency omega c should be at least 10 radian per second. The phase margin should be at least 75 degrees. Gamma n is equal to 1 for the noise signal such that the noise is not amplified or it will not be even attenuated in this case. For omega n bigger than 10 radian per second and gamma d is equal to 0.1. We have this for the attenuation of the disturbance. For omega d is smaller than 0.1 radian per second. And then we will verify the result using MATLAB to see whether all the requirements are satisfied or not. As the first step, we would need to draw the body plot for this system, considering GC of s equal to 1. We will have L of s equal to 1 plus 10s over s times 1 plus s squared. And therefore L j omega will be equal to 1 plus j 10 omega over j omega times 1 plus j omega squared. We have 4 components here, 1, 0, 1 pole at the origin and 2 poles at minus 1, omega equal to minus 1. Let's start to draw the body plot for the system. Here we have the amplitude plot and phase plot. For the first component, if we consider that it's the 0, 1 plus j 10 omega, the corner frequency will be omega will be equal to 0.1. Before that, we will have 0 dB, and after that, we will have 20 decibel per decade as the slope of the straight line. So this is what we have for the 0. Then we have the pole at the origin. For that, the amplitude will be equal to 1 or 0 dB at omega equal to 1. And the slope will be equal to minus 20 decibel per decade. So we will have a straight line passing through omega equal to 1 at 0 dB. And then we have the last term, 1 plus j omega squared. We have 2 indeed poles with the corner frequency of 1. Therefore, we will have the amplitude equal to 0 dB till omega equal to 1. And after that, since we have 2 poles at that point, we will have the slope of minus 40 dB per decade for the amplitude. And now we can add all these to each other in order to obtain the overall amplitude plot for the system. So until omega equal to 0.1, we will have the amplitude coming from the pole at the origin. And then we'll have the slope of zero dB per decade at omega equal to 1. We will see the the two poles at omega equal to 1, and therefore the slope will become minus 40 dB per decade. So this will be the amplitude plot for us. And over here we can see that the crossover frequency will be somewhere around 3 radian per second. In terms of the phase, for the 0 which is at omega equal to 0.1, at that point we will have pi over 4, and eventually the phase contribution of the 0 will become plus pi over 2. For the pole at the origin, we will have minus pi over 2 all the time. And for the two poles at omega equal to 1, we will have minus pi over 2 at omega equal to 1 and minus pi at the end. So this will be kind of the phase that we get for those two. And now if we add everything to each other, we will have the phase plot for the whole system. So we will start with minus pi over 2, then the phase will increase, it will reach minus pi over 4 almost, and then it will decrease, and then we will kind of follow the phase that comes from the two poles. In order to determine the phase margin, we can have a look at the phase at omega around 3 radians, and this will give us the phase margin with GC equal to 1. We also need to determine the dangerous zones for the disturbance rejection and noise attenuation. For the noise, we need to have the amplitude bigger than 0 dB for this range of frequencies. So the dangerous zone for the noise will be this area. For the disturbance, we need to have the amplitude of L of j omega being smaller than 20 decibels for the range of frequencies smaller than 0.1. So for this range of frequencies, we need to have the amplitude bigger than that. You can see that currently those two requirements are satisfied. The requirement in terms of the omega c is not satisfied because we need to have it at least equal to 10. And if we have the crossover frequency equal to 10, then you would see that the phase margin here will be too small. So as the first option, in terms of the controller design, we can think about the proportional controller. The proportional controller with the generalized gain of 10 will move the amplitude plot upwards by 10 decibels. So for the whole range of frequencies, amplitude plot will move upwards. Will be fine in terms of the noise and disturbance attenuation. Omega c will be also fine, but then we will have a very small again phase margin that we need to think about. In terms of the steady state error for the step reference, it is already satisfied because we have a type 1 system. And for the type 1 system, we already have the steady state error equal to 0. So we don't need to worry about that. Alright, so now I will show you the drawing, the body drawing that I did manually. I've done it in MATLAB and I will show you how it looks like. Here we are done with this part. This is also something that we already have discussed. Now if we assume that we use the proportional controller, omega c will be around 10 radian per second. Did I say something different? Yeah, omega c initially was that, but if we increase the gain, omega c will become 10. And at that frequency, we can find out the phase margin. We can calculate the phase of the L of j omega, which will be equal to minus 170 degrees almost, and the phase margin that we obtain will be equal to 10.85, which is much less than 75 degrees. And therefore, the phase margin will not be acceptable. Here you can see how the body diagram for the two cases would be. The one in blue is the original system with GC equal to 1. The one in red is the compensated system with GC equal to 10. In terms of the phase, they are the same because with that controller, we don't change the phase of the system. In terms of the amplitude, you can see that for the whole range of frequencies, the amplitude plot has moved by 10 or 20 decibels upwards. The crossover frequency is equal to 10, and at that frequency we see that the phase margin is equal to 10.9. For the original system without the compensator, omega c was equal to 3 and the phase margin was equal to 35, which is still smaller than what we are expecting. Therefore, a better solution for this system would be to use a lead compensator where we will increase the amplitude around this frequency. If we have a lead compensator with 20 dB amplitude for the high frequencies, and where we just introduce some positive phase with phi m here around that frequency such that the phase plot here moves upwards, then we will have a bigger, let me draw it in green. If this is what we could get with the lead compensator, the phase margin will increase and we might obtain what we are looking for. Okay, so therefore we are going to design a lead compensator. For the lead compensator, we will check the desired crossover frequency. For this example, the desired crossover frequency is already determined and it will be equal to 10. So omega c, which is desired, is 10 radian per second. And we will use the same frequency for omega m of the lead compensator. So omega m will be also equal to 10. We need to place the pole and zero of the controller properly. So the zero of the controller will be located at some frequency smaller than omega c. Before the omega c, maybe around here, we need to determine that frequency. We will have a zero here and the pole will be located afterwards. We'll have a pole here. How we can get the exact positions, we will go through the formulations that we have. In this way, we will be able to increase the amplitude around the crossover frequency by the given value and also inject some positive phase into the system. Okay, so here we have the approach for designing the lead compensator. Omega m is selected as 10 radian per second because this is the desired crossover frequency. Then for phase margin, we do like this. For the phi m, for phi m, we will take the desired phase margin minus the uncompensated phase margin, where we have GC equal to 1. And we will add some 5 to 12 degrees. This is something that we already have discussed. The original phase margin, which was the one that we could obtain by moving the amplitude plot upwards by 20 decibels or making the crossover frequency equal to 10, is already calculated and it's equal to 10.9. So this is obtained by checking the phase margin at omega equal to 10. The desired phase margin is already given to us. It's 75 degrees. So we'll have 75 minus 10.9 plus some 5 to 12 degrees. And out of this, we will get phi m equal to 70 degrees. With phi m equal to 70 degrees, we can obtain the value for alpha. Alpha is equal to 1 minus sine of phi m over 1 plus sine of phi m, and it's equal to 0.03. We have the value for omega m and alpha. Using these two, we can obtain the value for p, because omega m is equal to square root of z times p. Therefore, p will be equal to omega m over square root of alpha. And we will get a value for p, which is the location of the pole of the controller. The pole of the controller will be 57.73. We can pick a value like 57. And then we have 0 equal to alpha times p. Therefore, 0 of the controller will be obtained as 1.7. And as a result, the lead compensator will be obtained as 1 plus s over 1.7 over 1 plus s over 57. And here you can see the effect of the applying the lead compensator which we just designed. The graph in blue is the one with GC equal to 1, and the one in red is the one with the lead compensator. You can see that for the low frequency part, the amplitude remains the same. For the high frequency part, the amplitude is shifted by 10 decibels upwards. In terms of the phase, you can see that around this omega equal to 10, the phase has moved upwards. So the resulting phase margin is now much bigger than the original one, 86.3. But now the crossover frequency that we have with this controller is not exactly 10 radian per second, it's 5.92. And in order to make it 10, we just have a look at the frequency of omega equal to 10. The amplitude for the GC, GP or for L is equal to minus 4.72 decibels. So we need to introduce a proportional controller with 4.72 decibels to move the amplitude plot upwards, and then omega C will become equal to 10. And when that happens, the phase margin will be equal to 86 degrees, omega C will be equal to 10. We will be happy with both, and then the other requirements will be also okay. So the proportional gain that we need to introduce is 1.72, which gives us the 4.72 decibels. And therefore, the whole controller that we end up with, the lead compensator, will be equal to 1.72 times 1 plus s over 1.7 over 1 plus s over 57. And here you can see in blue we have the GC of s equal to 1, and in red we have the final controller. You can see that the amplitude plot doesn't enter into the dangerous zones for the disturbance and for the noise. We are happy with that. Steady state error is equal to 0 because we have a type 1 system. Omega C is equal to 10, and the phase margin is equal to 81.2 degrees. So we are now done in terms of designing the controller, and all the requirements are now satisfied. I think that's all for this video. I hope you have learned the steps that you need to take in designing the lead compensators or phase lead compensator. You need to determine two parameters for the lead, omega m and phi m. Once you determine this, you can obtain the location for the 0 and the pole. Omega m will be usually set as the desired crossover frequency, and phi m would be the amount of the phase that you need to inject to the system at that frequency in order to obtain the desired phase margin. Okay, so that's all. Thank you for watching, and see you in the next video later.